Hi, this is Adam Lehman from Hamilton County Conservation District in Ohio. The following video is from part 3 of a 4-part day-long workshop on estimating pollutant loads using the U.S. Environmental Protection Agency's Pollutant Load Estimation Tool, or PLET. The workshop was designed to assist natural resource managers with estimating load reductions for conservation projects, as is often required by important funding sources. Video from other parts of the workshop can be accessed from the Hamilton County Conservation District's YouTube channel. A link to that playlist is provided in the description of this video. Part 1 of the workshop covered the context of why tracking pollutant loads and their reductions is important and the status of those efforts nationally and in the state of Ohio. Part 2 of the workshop covered an introduction and a detailed walkthrough US EPA's new pollutant load estimation tool, or PLET. Part 3 was an overview of the methods and parameters used by PLET and resources for estimating those parameters. And Part 4 was a GIS and spreadsheet workflow demonstration for how to generate the needed parameters. For an example, agricultural treatment wetland project. Also linked in the description is a resources web page that was associated with the workshop. This web page contains lots of linked and downloadable resources discussed throughout the workshop. Thanks for your interest in the videos. This is really going to be geared towards folks that don't have a huge amount of experience with hydrologic or load modeling. So we're going to go through the actual methods and the parameters in those methods that we're entering into PLET. And importantly, we're going to provide resources to get them. And so even for folks that do have a little bit more experience with this stuff, we have a couple new resources that I'm really excited about. We've got a query that NRCS has developed to get us the exact information that we need, lightning fast, to build these PLET models. And we're also going to provide a universal soil loss equation topographic factor raster tool as well. So this is kind of our guide for the afternoon, and this is kind of PLET under the hood per me, and so don't get too overwhelmed. We're not going to be walking through this with a fine-tooth comb looking at all the linkages, but the methods here is going to serve as kind of the agenda for part 3 in the early afternoon. First, we're going to talk about curve number, and then we're going to talk about universal soil loss equation. And so that's what's going to happen this afternoon. This is kind of just going to be a general resource that we make available for you, but along with a lot of other resources. So we had the question earlier, where can we get resources for these parameters? And that's what we're all about providing here this afternoon. And so this is the workshop's resource webpage. And this resources page just has two things. It has a list of links and it has a list of downloadable resources. And it's pretty much ordered in the order that we're going to encounter them in the workshop. So these top 3 are the PLET website, user guide, login, all the things that we've already gone through today. And when we come back, we're going to start talking with curve number. And then so here's a resource for that. All right, welcome back, everybody. As promised, we are starting promptly and jumping right back into this third part of our pollutant load reduction estimation workshop. And this section is going to be focusing on the methods and parameters needed by the PLET model and some resources for them. So jumping right into it, the first method that we're going to look at is the curve number method. So the curve number method basically estimates runoff. And that takes the following watershed characteristics. It takes precipitation, irrigation, if that's relevant, land use, and soils. Okay. And so this is all about providing resources. And so we're going to jump right into the resource that I'm going to recommend for this one, which is NRCS's Technical Release 5, commonly referred to as TR55. So I'm going to be kind of jumping back and forth out of the slideshow and going to this website here. So this is the resource page that I sent you all to earlier. The link is in the chat. So you can head there now, and it's the fourth link down is Technical Release 55. And so what we're looking at specifically within Technical Release 55 is Chapter 2, okay? Chapter 2 is on estimating runoff with the curve number method. So we got a hot link here in the table of contents that takes us straight to it here. Now, right off the bat, what we see is, technical documentation, a bunch of equations, and a description of what the method is and how it works. And, I would encourage everyone to be familiar with this, because this is not an insurmountable task, right? We're talking about 1.5 pages of text, and then the rest of it is just, graphs and tables. And really the tables are the resource that I want to jump to right now. So we're not going to spend our time looking at the mechanics of how the curve number works. Just understand that high curve number means there's going to be a lot of runoff, and a lower curve number means there's going to be less runoff, okay? And so the PLET model, I can't see my tabs with the controls here. So the PLET model, as we saw earlier, right here on the inputs tab, you go down and there's, places that are already populated with curve number values where you can change them if you want. So for both the non-urban land uses as well as the urban land use breakdown. So if you look at these numbers in these various categories and compare them with our resource here, if you go down to table 2-2, and this table spans several pages with lots of different land uses listed here. And what you're going to notice is that those are the same numbers, right? So those numbers in PLET come from the same source as these tables, right? And so a question you might ask yourself is, okay, Adam, then why are you wasting our time pointing out these tables? And the answer is that, in some cases, there might be land uses that you, in your project area that you want to describe, that aren't included in PLET. And so I'll give you 2 examples that we're going to work through in the example in the later afternoon portion of this. And that is, I have this land use that is user defined, right? And that's a land use that I'm characterizing as hayfields, which is not a default non-urban land use within PLET. Okay, and so I had to come down here and I had to enter in these values under user defined. Another example is I have something that I called farmstead, right? And so I just picked one of these urban categories that I wasn't using, and I tried to pick something that had the most similar amount of impervious surface and might be expected to have a similar type of runoff regime. So I think I picked multifamily as my category, where I changed the values here. And so where did those values come from? They came from TR55. And so I think it's on the third page of table 2.2 here. We've got this meadow category, which says continuous grass, protected from grazing and generally mowed for hay. That sounds like what I'm looking for. And then there's this farmstead category here that consists of buildings, lanes, driveways, and surrounding lots in a farm context. So that's what we got here. And the thing to note about these tables is that they have two components. They've got land use and they've got soil. So these are hydrologic soil groups. We've got A, B, C, and D. So there's only 4 groups. And if you come up here to the top of the section where it's describing the method, we see here that soils are classified into 4 hydrologic soil groups, A, B, C, and D, according to their minimum infiltration rate, which is obtained for bare soils after prolonged wetting. So that's what it means. But in reality, you're just going to be looking for your hydraulic soil group for whatever soil types are located in your project area. So, we're looking for soils data and we're looking for land use data in order to get these parameters that we can then use to look the values up in these tables. So let's go back to the slideshow for just a minute here. We're going to start with the land use side of this. So what are our sources for land use data? There's basically 3 ways to go about getting land use data. You can get a national land cover data set. And I'm going to suggest that a convenient place to go and get that is USDA's Geospatial Data Gateway. And I'll give you a real quick run through on that in just a minute. You can check with your local county or municipality. I'll tell you, in my experience, they don't tend to have unique land use layers. What they might often have are impervious surface layers or various components like road polygons, houses, things that you can piece together. And so if you're modeling in an urban context, you might be able to piece together those impervious areas, maybe digitize a forest stand or 2 and call the rest lawn. And so that's an option. Now, this workshop is really geared for folks who are trying to come up with pollution load reduction values for their BMPs that they're trying to get funded, right? So a lot of these are going to be kind of small site scale projects. And so if it's a pretty small project, hand digitizing the land use over an aerial photograph is something that I would highly recommend. It's going to greatly increase the degree that you can be confident in the data that you're feeding into the model. And I'm going to show you some examples of how national data sets have lined up with our example that we're going to work through later. And they're not looking great, right? But another bonus of digitizing it yourself is that you can, categorize and classify the land use in the ways that are going to conveniently fit what you need to enter into the PLET model. So just real quick, back to the resource page here. The next link down is USDA's Geospatial Data Gateway. And so if you want to get data, I recommend clicking this giant green button that says Get Data. And it's going to want to know where you want data from. So you can select your state. I'm going to type O for Ohio. And then you select your county, H for Hamilton County. Click it over there. And then you can see the next question is, what kind of data do you want? And there's tons of data here. And we're not going to go through any of that. We're just going to stroll down to the land use. And you can see that you've got 2 choices. And these are both. So we have the National Land Cover Data Set. You can click the little I here and read about it, and you see that it's the 2019 data set. So that's the newest one. And it's got 30-meter resolution for raster data. Similarly, we've got cropland data here, and it also has a pretty large scale, or actually small scales, low resolution data with 30 to 56 meters. And so we'll say we want the national land cover data set. I click continue. It acts like we have all these options for format and whatnot, but I've never actually been presented anything that I can select or change. So you're just going to hit continue. You're going to enter your email address here, and once you hit continue, it's going to send you an email. This time it says it's going to take about 5 minutes, and so if I press place order, I'll get an email in 5 minutes. I click the link in the email, and it's just going to start downloading. So that's a good resource for getting national land cover data. Now, the other part of this is the soil data sources. Okay, so soil data, we're going to be talking a lot about. So the next method that we're going to be talking about is the universal soil loss equation. And so as you can imagine, we also need soils data to feed that. So I'm going to push back sharing the resources for a bit. And first, we're going to bring on Steve Baker, the state soil scientist from the Natural Resource Conservation Service for Ohio. And he's going to give us an introduction to the universal soil loss equations and the various parameters associated with that. And then his colleague, soil scientist and soil database manager, Jeff Glanville, is going to talk about the accessing that data. And I'm super excited about this because Jeff has created a custom query that we can use that's kind of specifically extracts the data off their online resource, and is going to give us a table of all the things that we need with this custom query. So we'll hear about that, but first I'm going to make Steve a co-host here.
So I'm going to kind of forego the presenter view because I find it very difficult. I'm just going to try to move this over a little bit. So USLE part of the presentation is pretty short because quite honestly, we don't use it anymore at NRCS. And there's a lot of things that are kind of lost to the annals of history there, but I can tell you a few things on it. And that's where, the USLE was one of the first nationwide ways to try to predict average rate of erosion for crops, erosion for crop and management practices. So it uses inputs from soil types, also rainfall patterns and topography. It's a fairly useful comparison against allowable erosion. And what we're saying on that is a t-value. You've probably heard it somewhere along the way if anyone runs Russell also. And the t-value is the tons per acre per year that soil scientists, when they map these soils, said, well, that's probably a reasonable amount that you're going to lose because, whether it's a natural system or heavily farmed, you're still going to have some erosion losses. They just vary based on land use there. So if you see t-value in your soils data, just remember that's what it is there. And then it's a relatively straightforward equation in the sense of tons of soil lost per acre per year. The A is by multiplying out the rainfall runoff factor and soil erodibility, the K. We'll talk more about K later. The LS, which is the slope and slope length factor there. And that's, again, another ball of wax we'll get into. And then, kind of the two unknowns to me at this point are cover and management factors and practice support factors. So they're out there, they exist. Ag Handbook 504, is it? I can't think of the right one off the top of my head, but they cover more of those factors. But there are factors already built into PLET, I believe. Is that correct for the C and the P?
We have resources for C and P up on the website or on the resources page. So we've got, let me just look at it here while I'm talking. So we have the agricultural handbook that you alluded to. So the first one is the universal soil loss equation. That's 536. And that has some values and you can use that for P. The C values are state specific. And so those are downloadables. We've got an OSU extension bulletin from 1979, which is going to be super helpful for basically non-ag stuff, because they have an area where you go by different vegetation with different strata. I think it's table 10 in that document is what I would recommend for looking at things like, what about a honeysuckle patch, or what about lawn? And then there's also this Ohio Russell factors document from 2002, and that'll give you a little more up-to-date C factors for agricultural contexts. But generally speaking, the P values are kind of limited to very specific practices like contour farming, terrorists, things like that. So those might be a little less common. So yeah.
And so for the R factor, where they're putting, and thank you, Adam, by the way. So on the R factor, one thing to mention is they are a frozen value, at least for NRCS, because these were developed for the USLE equation, which has been supplanted by Russell 2 and other things that are in the works. But just worth mentioning, I think Rick Wilson brought it up earlier, that we have a lot of data showing that rainfall intensity has moved up over certain time periods, and just kind of wanted to mention that's kind of how that works there. And the way we did it at NRCS was we actually have the R factor as a frozen for USLE purposes there. So moving on from R factor,
Steve, I want to add one comment there, and that is that R factor is preloaded into PLET, and it doesn't necessarily it's not necessarily the same as the county R factors that you sent me, which makes me think that they're specific to the HUC 12 that you have to load in through. And so that's already there. Someone can go down that rabbit hole if they feel so inclined.
Yeah, I would feel pretty confident with using whatever's preloaded into the tool. There's obviously been some thought into that, and digging further may not be worth it. And out of the factors for USLE, the one I wanted to cover the most though really was K factor. And the K factor is really talking about how easily is that soil detached and moved down slope by water, both sheet and rill erosion, and to some degree also concentrated flow. And the best way I can explain it is to think about this as a scale of 0 to 1, 0 being the least likely to detach, 1 being the most likely. So, sands tend to be at like a 0.1 all the way up to most of Ohio soils that are silty in the surface anyway. They'll be somewhere in the 0.36 to 0.49, somewhere in that general range. So, if you're dealing with highly eroded areas, the K factor may actually be fairly low because we've moved into clays that are less likely to detach and move. So they'll be down on like the 0.2, 0.3 part of the scale, that kind of thing. So K values can be pulled from the soil survey data. We have them by horizon, and we'll discuss that a little bit more when we get into Jeff's query, and you'll see where it comes into there. But I know that's a factor that you need to put into other work there. So Adam, do you want me to do the LS factor stuff now, or do you want to kind of end the USLE part?
You can do the LS factor now, and I'll just pick back up with the raster version after Jeff's talk.
Okay, that sounds fine. So let me get out of that one. So the LS factor, we saw that in the formula there. The LS is actually, again, devised as part of USLE, where they're taking slope and steepness, slope length and steepness, I should say, together to come up with a factor that gets multiplied out, though. Ag Handbook 703, which is the Russell Handbook, goes into a lot of depth there. But one of the things that they mention is there's almost an infinite combination of how many slopes and slope lengths are out there. This is where, depending on your scale, you have to just find the one that fits what you're working on, whether it's a field or it's a watershed. One way or another, you're going to have to come up with a number to get that LS factor there. So to try to illustrate that a little bit, here's an example of a block diagram kind of showing your average glaciated area there. And there's a slope length coming from the top of the hill with some trees. You can see that A right there coming down to a concentrated flow area. That's one slope length. There's D over here showing from the top of this maybe moraine or something like that, moving down to, again, a concentrated flow area. There's in complex slopes, you can come up with a lot of these. So, for us, what we look at is we're going by farm field. This field overall, it's maybe not the steepest part because that may not be representative of the whole area. So we call it a critical area measurement. You're trying to look for what makes up the most of the field and is limiting still. Again, that slope and slope length. And the slope length is defined as where would water start to flow and then where does it end? That's why D is probably the better example right here, where you can see water would begin at the crown of the hill and it's going to be intercepted right along here. We'll assume that's a bench break or something like that. So how are we doing on that so far?
Sounds good to me.
All right. So, as another example, looking at some unglaciated areas with a little bit of difference to that, you may be coming up with a couple different numbers there. And, on this particular example, it looks like here's about where the water would shed. You're picking up at a break. So there's one length. Here's another, where maybe there's a break earlier. So at the end of the day, you may have to do several of these and come up with an average to get the slope length of where that water starts to shed, where does it collect. But, it's fairly, I don't want to say open to interpretation, but you do have to think out what you're doing there and what are your combinations and what is a good overall number to use for that. So once you have your slope length, and then of course the slope percent, most people would shoot that by clinometer if they were in the field or an Abney level. Nowadays we can do that by LiDAR, we can do slope maps and ArcGIS. There's plenty of ways to derive the overall slope, but all we have to do is use this section here to figure out your actual LS factor by taking the slope percent across the top. I cut this particular one off at 16% slope, just because in my mind, I was thinking farming. It does go further, and I believe that's in your resources, Adam. But, let's say it's a 2% slope with 150 slope length. It's a 0.23 LS to plug into your numbers there. So really that's all there is to the LS, is using the chart to come up with that number. And I'll be honest, I'm not really sure how that gets calculated out into the PLET, whether we have to plug that in or if that's picking something up on its own there, but just wanted folks to understand that basis.
Yeah, you just enter an LS factor into the PLET for each land use, and we're going to show folks where that goes, and they've actually already seen that from Tetra Tech this morning. The one thing that just kind of generally for folks who aren't very familiar with the universal soil loss equation that I want to emphasize is that this is an estimate for sheet and rill erosion only, not concentrated flow. So when, when Steve was showing his slope lengths stopping kind of before you get to a concentrated flow path, that's because that's where those slope lengths end. They can also end in a area that starts to deposit eroded sediment, right, Steve?
Correct. It is only sheet and rill there. That's a good point. And the same is true for Russell also. If anyone's moving on to Russell for anything else, it's strictly sheet and rill erosion there.
For folks that aren't familiar with these terms, could you give a real brief overview of what the differences are between Russell and USLE and Russell 2 and so on?
Sure. So USLE, like we were mentioning before, it is I wish my agronomist was here to explain this better than I can, but USLE was designed, again, as the first way to kind of quantify sheet and rill erosion. And from there, they decided to move on to the original Russell, revised universal soil loss equation there, and Russell 2, and I don't know all the in-betweens on those, but the main thing in Russell 2, if I understand it correctly, is that the program, for one, is a lot more in depth in the sense of it has input factors for different machinery and how many passes, and it's really taking much more into account than the USLE ever was, as far as pulling together numbers for ground disturbance. Especially, it takes into account the type of tillage implements that are used, if they are, the type of planting equipment, if you're knifing in fertilizer, all of that goes into that. And it also has more of a daily function to it based on the R factor, as opposed to the USLE calculating it out on a yearly loss. And Russell takes the daily losses and sums them into a yearly, and Russell 2 now. So Russell 2 was just an upgrade to the revised universal soil loss equation. Did that help?
Yeah, and just to emphasize that, we need the parameters that are associated with annual soil loss for PLET, because that's what PLET produces. It produces average annual loads. Okay, so we got does that conclude your section, Steve?
Unless you wanted me to take care of the Sergo download before Jeff gets into the data access queries.
Okay, well, I tell you what, you guys got 15 minutes left, but why don't I just kind of jump in here? I think it does make more sense for me to just show that toolbox real quick. And then we'll get you guys back in for your next 15 minutes. So let me share my screen and just point out. So, like Steve mentioned, let me get these out of the way. Like Steve mentioned, if you're measuring, if you need a slope length for, a BMP at the edge of a field, and you got like a nice rectangular field with a uniform slope, then just going out there and measuring one slope length is no problem. But when you get into more complex landscapes, it becomes a lot bigger of a task to go measure tons and tons of slope lengths and trying to come up with area weighted averages. So in practice, this is often done via raster, right? So right here, I have this LS factor raster toolbox, and this is for ArcGIS, and it's basically a tool where you can enter in a DEM. Let me where you can enter in a DEM, and it's going to spit out two things. Or you're going to enter in a DEM, you're going to enter in your project area, and it's going to spit out a raster data set with that's just LS factor. And it's also going to spit out a table, and that table is going to be either the weighted average LS factor for your whole project area, or if you enter in a land use shape file, then it can give you the average LS factor for those given land uses. So let me just state that this is a tool created by me. No one warrants this. This is not associated with EPA or NRCS or even the district. This is just a tool that I am providing to help people out with. And you can go here and I got this description here that kind of walks you through the various inputs. And I'm just showing you that there because if you actually click on the tool to open it, I lost all the spacing in my in between my paragraphs, so it looks a little messy, but you can read it in either direction. And so we're going to go through this in more detail later, but just know that you have this tool. I will say that there are multiple methods, and there's an active literature around the different ways to calculate LS factor for raster data sets. And they can result in significantly different results. So I used kind of a simple, commonly used one. It's not the only answer, but it's a tool for folks who don't have a lot of experience with this, but who need to get an LS factor. And so just to kind of show you the workflow here, I'm not going through this, but it's just to show that there's a lot of steps that are needed with this and some math that goes into it. And all that math you can find in those handbooks that Steve was talking about earlier. But so this is here as a resource. And with that, I think we'll give it back to Steve to talk about how to download data. While Steve's getting that loaded up, I got a request here. Where can you share the metadata for folks on QGIS who want to create a similar tool? Yes, I'll tell you, it doesn't help you much if you don't have access to ArcGIS, but the metadata is the fact that I built that with that model builder, so you could go look at that flow chart and click on the tools and see what's everywhere. I am open to looking at doing something similar for QGIS, but we don't have that right now. Sorry, Steve, go ahead.
No, you're fine. So getting into something we actually do a little more of, and that's talking about soil survey downloads. So, running through this here, if you go to the web soil survey, and most times I just tell folks, Google it, nobody wants to type all that in. If you don't have this link around, it'll find you. So, you're looking for full county data. So, by default, web soil survey takes you to where it wants you to define an area of interest, maybe go out and draw something in. In this case, we're actually going to go over to the download soils data tab over here. So web soil survey, if you haven't used it a lot, there is a tremendous number of tabs. It's easy to get lost, but it's there. So once you go to
Steve, can I just add, I just realized that I never linked web soil survey to the website, but it's super easy. If you Google web soil survey, it will be one of the top 2. So sorry about that. Continue.
Oh, you're fine. So, once you've gotten to that download soil survey, soils data tab there, you're actually going to go to your soil survey area. It looks like I lost an arrow somewhere, but Surgo is basically the county base of soils, and that's how all of ours were published in Ohio. If you go to other places, you might see where it's not county based, but Ohio is this way. So once you click on soil survey area, it gives you options down in here, and you can set your soil survey proper state and county there to do the download. Let me see if I can expand this a little. Oh, that's better. So you set to the county and the state, and there's the download link right there. So once you hit the download link, you just need to save it to wherever you're going with it. I have a geodata folder. You may have something else, entirely up to you. And you're going to unzip the folder to there because that's how it comes to you. Once that file unzips, I think this is an important part to run through real quick though. You're going to have several folders, the spatial and the tabular data. And I did this according to Arc Pro. Arc Map's slightly different, but Jeff or I are always available. You can call us if you're having trouble with this. And let me look at the spatial data breakdown there. So when you open that folder, you're going to have your typical shape files in there. The soils polygons are the actual boundaries to say this is the limits of Miamian soil or not Miamian soil. Then there's the soil labels as points. We never really use that, or the boundary. Most of these don't get used a lot. I will mention that down here there are special features like gravelly spots, things like that. Those are fairly useful just to pull them up so you kind of know any base information that we put in the soil survey for you. So main thing though is knowing that the soil's polygon is what you're mostly going to be using for this. So when you look at it in the data or in the ARC catalog, it's going to look more like this. So this makes a lot more sense where the MU 061, that's the soil map units as you would want to see it. So one thing I wanted to show too was once you've brought in that shape file of the soil MU, then you have the ability to look at all of the base mapping there. And when you open the attribute table, there's not a lot in the attribute table there. It's basically the area symbol, map unit symbol, and a map unit key. And I put that in highlights because map unit key is pretty crucial. That's a number that helps tie together other data. The keys don't change, whereas the map unit symbols, if you're working across county boundaries, can be the same for two different soils. So that's kind of your unique identifier to the map unit itself with the symbol and the name and all of that. But anyway, this is all the base data that you get. So under the tabular data, now I got to make this a little smaller. Under the tabular, you have lots of text files. This is where it's dumping out all of the parent-child tables out of NASIS, which is the tabular side of our data. And that you can bring those back into a GDB and allow joins using that MU key, then MU key down to components and all that. That becomes a real pain real fast. So it can really clutter up your data because all these columns start joining into that attribute table and you have a real issue there. So that's what kind of led us to say, this can be done, it's possible, we'll be glad to help you with it if you need it. But what Jeff's going to pick up with about the custom query is a lot easier because once he dumps that data out, you can use that MU key to match up your tabular data to the spatial and get only the columns you're looking for. So Jeff, with that, I'm going to stop sharing on this one and I'm going to allow you to pick up. Jeff, if you can't get that going in the name of time, I can just jump in and take this.
All right, Steve. Well, maybe you can just take it, and if he's able to figure it out, he can hop in,
Yeah,
anytime.
No problem. I'll go ahead and pick up here. So everybody can see that screen, I assume. So like we were talking before, instead of doing those big joins through attributes, we do have soil data access, which allows us to do queries on the tabular side of data. Hang on, I'm going to have to tell Jeff not to talk anymore. All right.
All right, he's muted.
Great. So on the website here, Soil Data Mart Access, that one, I believe you can Google it also and it will show up, not a problem. And Jeff's the one that set all this up here, so bear with me. I don't know it as well as he does, but the gist of it is you're going to submit a custom request for soils tabular data. And he goes in to show just a screenshot there that the query shows up as a box down there for SQL, and you're going to enter the query into here. So on this particular one here, you would just copy and paste. Whoops, I just moved it. Oh, Control Z, it's my best friend. You would copy and paste this into that query box, just like that. Do the immediate results there. And then it'll pick up as a table. From there, you just copy and paste that into Excel. You can also do a queued query. That one I'm not as familiar with, but you can do it. And really just the copy paste does work pretty well into Excel there. And then one thing he mentioned is it will always come up and say you're in the queue. It's going to take a minute. A lot of times it really doesn't take that long. But you also will get an email that tells you it's ready to download. If you do the queued query like we were talking about before, most folks will do the instant results and get something more like this, where they can just copy paste, but either one works. So the main thing about this query is it's going to bring some things out that you're going to need if you're being more exact into the PLET tool, most specifically the hydrologic group, the K factor. It gives depths on there also. So this is a way that when it kicks out, notice it has the MU key. So from the map unit key, you can use that to join data. And again, from the Sergo we downloaded in the last file, now we can go ahead and join MU key to the table that you have here. So there is a link to query help there. And, you know, again, Jeff's available. NRCS can help you with this, more so than I can anyway. And, you know, there's a lot of homepage stuff there that you can go through to learn more about the data query access, because it's a powerful tool to pull down just the data that you want, as opposed to that joining into a geodatabase through all of the other tables and getting a lot of data that you have to sort through. So in a nutshell, just to recap this one, the main thing is that you're going to go to the data query site. You're going to use this query. And then once you have that, you can put it into a table, bring that into your GDB, do a join, and now you can go back into ArcPro or ArcMap, and all of that information will be in your attribute table. If you're trying to do something where you're making your own custom AOI and getting the dominant hydrologic soil group or something along those lines. So I'll stop for questions.
Yeah, Steve, I want to add a couple things. So I'm glad you got this slide up. So we've got this SQL statement here that we're just copying in. And if you look down to it, says where LDOT area name like, and that says Hamilton County, Ohio. And so this is going to get that information for Hamilton County, Ohio. And what I'm assuming and asking is that this LDOT area name is the soil survey area. So all in Ohio, they're all county based. And so you could change that and just say Butler County, replace Hamilton with Butler, and it's going to return a table of the same values for Butler or for Lake County or for Logan County. Is that correct?
That's correct.
Okay. And then the other thing I just want to point out, will you go to that next slide? So there's that default right now. It's selecting intermediate HTML results for fast table viewing. So that basically just opens up, you know, a table in your browser, and then it's just super easy to you just copy the whole thing and paste it straight into a spreadsheet, and it's that simple.
Absolutely.
So yeah, so I'll shut up and let other people ask questions at this point. Maybe just shout them out if you got. I'll also add that we have that query is in a text file on the resources page. So you can just download that text file for easy copying and pasting. And all you got to do is change your county name.
Yep.
Well, we got a couple minutes, Steve. I'll ask a question. Will you kind of explain to people how soil survey areas work? And so if we got folks from Kentucky or other states that are going to watch this, how might their areas differ from counties and how can they modify that query accordingly?
Oh, that's a great question. I believe what you would have to do, and I'm trying to think of any that aren't county based in the east. For the most part, they are. I know in West Virginia, Tucker and Northern Randolph County were together. And at that point, you'd have to go back in and use, Jeff mentions it down here with the wild card character there. You might have to go in and put Randolph or like Randolph County, something like that. I'm not really sure how to do that though, to be honest. I haven't had to deal with it in a long time. If my
So
best
maybe
advice,
a fair thing is if you're in a place with a non-county based soil survey area, you just need to call your local NRCS office and ask.
yes, I would call to the state office directly, find the state soil scientist and call them because they will know the trickeries of all of that for you to decide how to ferret that out. Again, I think it's a fairly uncommon thing, but if you run into that, they can definitely help you.
Great. Okay, I think we're out of time on this. Is last call if anyone has a quick question.
I just want to, Adam, this is Chris. I just want to jump in and remind folks that all this business with soils and getting this information was to be able to parameterize or choose values for the K factor and the hydrological soils group. They're important in the PLET modeling and and potentially texture. What anything else that's critical to the PLET modeling that I missed there?
Yeah, well, let me just share a PLET for people to look at here. I gotta get these, always juggling windows here. So here we're on our inputs page, right? And so each watershed only has one hydrologic soil group. So we're going to need to get a area weighted average hydrologic soil group for the whole watershed. We'll talk about that later. And then we come down here and these are all our universal soil loss equation parameters. So R is preloaded. P, you're only going to change it if you're doing very certain agricultural practices. C value, they give you recommended values, but we have resources up online that I recommend you take a look. But this is basically going to be driven by your land use, right? So you're going to say, okay, I got a land use of this, and this land use has this C factor. But other than that, we've got our K value here that's coming from the soils data. And then the LS factor will come from probably that raster data set, maybe field measurements. The only other thing I would add is they have also added texture. And that's really important for our streams and gullies, right? Because different textures have different bulk weights, right? So you have to select a texture here. And so say I got sandy clay loam, it's going to populate this with this bulk weight, and you can change that. But we have textures for different soil horizons or different strata, right? So the table that you're going to get from that is going to have for a given soil type, well, down to 20 centimeters, it's this texture. Below 20 meters, it's this texture. And so if you're looking at an eroding stream bank that's like 20 feet high, you might want to look and come up with a weighted average for what those different textures might be. And so, you could say, all right, well, it's sandy clay, but then below that it's sandy loam, and then you see the two numbers that pop up here. And so maybe you just average them and kind of change that factor right here. But that is the extent of kind of how soil parameters interface with PLET.
And Adam, can you remind us what PLET is populating these numbers with as default? Are they using
Yeah, I'm going to go
Sergo?
into so this is, recall that you have to enter a Huck 12 to start your Huck project. And so all of the pre-populated areas are going to be area weighted averages for the entire Huck 12 watershed. And so I will say later that, in my opinion, in my strong opinion, it is not appropriate or good practice to just accept those preloaded average values for an entire Huck 12 when you're assessing a 20-acre area that could have very different local characteristics. And so that's going to be something that we're going to talk about a little bit later in the afternoon.
Great, thanks.
Okay, so we have moved beyond curve number here. We have hopped over the topographic factor raster, and we are back here working our way down the methods part. And so this morning there was some discussion about delivery ratio, sediment delivery ratio, and you can't change that in PLET, so I'm not going to spend much time with it, but I'll mention that it is driven by watershed area. So the larger the area, the smaller the proportion of field eroded soil that is delivered to the stream or whatever the outlet of your model is, right? So, when we're modeling soil sediment from gully or stream erosion, there's an assumption that that all just falls in. So it's 100% delivery ratio. But if we're measuring it from erosion from the landscape, from the universal soil loss equation, that sediment delivery ratio is applied. So just keep that in mind as you are making your watersheds and deciding how big they are. And I'll talk a little bit more about sizing our units of analysis later as well. The next item down are these concentrations. And so you can recall on our PLET here, we've got right here our percent nutrients in the soil. And so this is something that, particularly in an ag context, you might have local data from soil testing. And so you might have something that you want to update this with. Now, there's also these runoff concentrations for different land uses. And if you want to look at the urban table, then you got to go to the urban BMP's tool. But it's the same thing. You can kind of double click here and change it. This, I would say, is maybe a little harder to come by, appropriate local values for, what are termed as event mean concentrations for a specific land use. I don't know of good local data, and my impression is I'm using the PLET tool, so maybe this is just part of that method. But you can certainly, if you have that data, you can change it here. And as always, good local data is preferable. So gullies and stream banks, I've kind of talked about this a little bit already. These come from the Region 5 model, and there are two basic things that I want to highlight. There's one thing I want to highlight for each of the two methods. So for the gully, basically it's just saying, it's asking for the length, the depth, the width of your gully. You're getting the volume of what has been lost, and it's calculating, the amount of sediment and the nutrients associated with that. But where the rubber hits the road in PLET for gullies is this one right here. It says years to form. Okay, and so what's clearly happening here is the assumption is that the rate of gully formation in the past is going to continue in the future. And so, you can use your expert knowledge of the field to try to assess if you think that rate is appropriate, and you can, tweak the numbers a bit to represent that, as long as you're transparent about it. But so how do you know, years to form on a gully? And the easiest tool I can think of is Google Earth Pro. So I've got this example here. For people who don't use Google Earth, the Pro is free, right? So it's just Google Earth now. They're all Pro. But here's a gully that's in Claremont County. And if you go to the view and you click on historic imagery, you can just really easily click backwards. So right now we're looking at this month, brand new image, right? And we can click back and drag back, all the way back to 2012. And I don't really see it there. Let me keep going because I know it's still there. Well, we can kind of see it here. It gets obscured in this tree line for a good long time. And so this gets to the point of, okay, well, what is the current rate that it's advancing? And is that to be expected in the future? So something I might do is I might click forward to when this thing actually starts growing. And, maybe you just measure that portion of it from that where it started growing to where it reached now. And then you can apply the years that it took for that to happen, and that will give you a good rate for simulating future loading, right? So here we've got October 2013. It's still not moving, so maybe we'll wait a little bit longer. We're in 2018, and it starts moving here around October 2018. And you can see that over the next 3 years, this thing really starts trucking. And so to me, if you want to talk about, it's another question if future advance is going to equal past advance. But if we're trying to get the current rate of gully formation, we really want to look at just the last few years for this example, in my opinion. So that's what I have to say about gullies. On stream banks, it's a little bit different. On stream banks, we're looking at a given stream bank. It wants the height, it wants the length, and that gives us the area of the stream bank. And then it asks us what the lateral recession is, and that is how much it is moving, it is eroding, in towards the bank, away from the stream. And so that's going to give us volume because that's in units of feet per year, right? And so the length times the height times the lateral recession gives us volume per year. Again, we have our soil texture data from that query, and that's going to give us our load. But the question becomes, how do we know how much that lateral recession is going to advance in a year? And that's when you come over here and you click on this more info. And this is what we have to go on, right? This is a method that came out of the Region 5 model. And if you start chasing down the references, you quickly find that this table was created from a personal conversation with L.J. Steffen in 1982. So take from that what you will, but what we have here is these descriptions that describe an existing conditions of a bank. And it has things like, how much rooted material you see. Is it overhanging? Is there any rilling? Is there any gullying, any sloughing going on? And from all that, you can come over here and say we have a bank that we think lines up with severe. We get this rate, but it has, a bounded range. So we can re-put anything in here that's within that range. But again, if you have some expertise about, the erosion in that local area, in that specific stream, maybe none of us have a crystal ball when it comes to how much the stream's going to erode in the future. So perhaps, just following this method might be the best way to go. But if you feel like you've got some expertise and know best on this, I wouldn't be shy about, making it fit and putting whatever rate you feel like fits, as long as you're transparent in what you've done and you explain to anyone who's using or assessing your model what you did and why you did it. Another tool that you might want to use, Roskin's BI Bank Erosion Hazard Index. I got like a 6-pager linked to the resources page. All that's going to give you is it's going to give you some things to consider, right, about how bad the erosion is. So it's similar to those descriptions. It's not going to tell you how many feet per year it's going to erode, because none of us have a crystal ball, but you can start to judge severity with these various tools, so that you can, feel like you're making an informed decision. And with that, I'll just point out that, what you're entering into PLET is not an entire stream, it's a stream bank, right? And so if you don't have much erosion going on in your banks at all, and you don't think that it's going to make a significant difference to the loading of your watershed, you might not include it at all. Or you might just have a couple outside bins that are starting to erode pretty badly, and you just want to measure the length of those and the height of those, and just add those to your model. And what I want to point out with this photograph is, where might you draw that line? Well, I kind of see a line right here where I feel like downstream, the erosion problem is more severe than this upstream portion, where we've got some vegetation rooted in the bank here, though it might still be pretty bad erosion going on up here. It's not nearly as bad as this area where we have sloughing in gully formations happening. And so I think that's about all I have to say about stream and gully erosion. Let me check the time here. I think we're doing pretty good on time. I think this is a important issue. So I'll pause here to see if anyone has any questions. I'm going to stop sharing so I can actually see my Zoom interface here. So I'm looking in the chat for the first time in a long time now. Can you do a search by a polygon instead of by a county? And I assume that that is a question with respect to the query tool for getting soil data. And I would replace the word county with the word soil survey area, but it's always a county in Ohio. And I would say not with that current query that we have, but I would encourage you to, like Steve said, call your state NRCS office and see if they can help you out with modifying that query. Another question I've got here, would those concentrations be annual averages? And so I guess that was with respect to the event mean concentrations, or let me pull up the PLET again and share my screen. So the answer in general is everything in PLET is average annual, right? PLET does not output monthly or storm event based loads. It only outputs average annual loads. And so, but these concentrations in runoff, it's an event mean concentration. So it's not an average annual, but if you look up here, you get this rainfall correction factor, rain days correction factor. So basically, and you can read up more in the PLET manual about this, but it divides the rain event for the year into like an average number of rain events. And then that event mean concentration, in my understanding, is applied to that. And then it's summed up for the year. But again, I'm not Tetra Tech. That's my understanding from reading the manual. And I would encourage everyone to read that manual if you're going to use the tool. It's not a huge one, and it's very well written and well organized. So I encourage you all to take a look at that.
Hey, Adam, I would add to that those are just expected concentrations in surface runoff from whatever that land use is. So just think of it that way. If you've got any stormwater sampling data where you've composited over a storm event, which often folks have in urban settings, or from edge of field monitoring sites, you could take that information and put it in there.
Just to conceptualize PLET a little bit, it's helpful to understand that your loads are really kind of divided. You can stick them in two buckets. There is this kind of event mean concentration data, which is basically driven by the amount of runoff that's from the curve number, and then there's average land use based concentrations. And then you got septic systems and animals, and those all have, per animal or per system, a certain amount of loading that's associated with it. And so that's one bucket of stuff that gets thrown out and produces a load. The other side of it is the soils, right? So we estimate the erosion from the universal soil loss equation. We use our delivery ratio, and that creates a sediment load. And then that sediment load also has nutrient and BOD too is related to that, where that will add in more of those loads based on the sediment that comes in addition to it. So you can think of it as, the dissolved constituents here in the mean concentrations. That's the way Region 2 describes it. And then you add to that your sediment associated concentrations. All right, another question, it looks like related to stream bank erosion, is would root wads and dead wood in the bank like that be much less erodible in the future? So, I mean, that's not necessarily a modeling question. It's a question of, do root wads add some protection? And I guess generally I'll throw out a sure maybe, depends on location. But again, you have to assess this as, someone who is familiar and understands the stream bank erosion risk at that site and come up with that lateral recession rate in feet per year. So, the model's not going to do it for you. You got to kind of, just like you got to come up with your BMP efficiencies for items that are not preloaded into PLET, you're going to have to come up with how much the stream's going to erode in the future. Because, EPA certainly doesn't have a crystal ball for streams they've never seen. And so we just have to do the best we can.
And Adam, for the root wads and the dead wood addition, if you were going to try to simulate that somehow in PLET, would that be done through the stream restoration BMP calculator?
I don't know of any BMP that looks like that, but again, I'm not Tetra Tech. So, but if off the top of my head, how I might think of doing that is just creating two models and then changing the lateral recession rate,
Oh, I
right?
see.
And so,
Ah,
how much does that root watt change that? Who knows? But that's what we're tasked with. Okay. Anything else? That's great. We're running 2 minutes or 5 minutes ahead of schedule, and I will take it because I need it in the next section. So I'll start with a real quick transition. And so for BMPs and BMP efficiencies, I think that got plenty of attention this morning by folks that are much more knowledgeable than me about it. So I'm going to kind of leave that at its face value and revisit this, the fact that this afternoon we're going to be working through a proposed treatment wetland example that is meant to treat non-urban land uses as well as a little bit of urban as well. And so that's not available in PLET. And so that's when we have to come up with our custom BMP. And so for the custom BMP, we have to come up with efficiency numbers. And so this means that we basically have to dig into the literature and find defensible numbers. And then when you are submitting your model and reporting on it to, the state grant folks or whoever else, you gotta be transparent, tell them what you did and tell them why you did it. This example that I'm going through is for a wetland that I applied for H2 Ohio funds for. And this is what I did. And I used these efficiency factors, and they came from the Center for Watershed Protection's Stormwater Retrofit Practices Manual 3. And so they had 40 monitoring studies that they assessed. And those studies were uploaded into the National Pollutant Removal Performance Database. That's also a Center for Watershed Protection project. So you guys can Google all that stuff and get this. But this is kind of the table from the appendix here that gives the performance of stormwater wetlands at removing various pollutants. And so we've got total suspended solids, which we can use as kind of a surrogate for sediment, right? It doesn't, I suppose, include your larger, coarser constituents of the sediment, but that's fine. That makes it conservative. And so they're saying 70% of sediment is removed by the median, was the median removal rate in these 40 studies. So the low end is the 25th percentile, right? The first quartile. The high end is the 75th percentile. And so it seems to me that using the median value is a defensible way to go. Now, it sounded like from Eric's talk this morning that he's talking to a lot of really smart people trying to nail down what more appropriate efficiency values may be. And who knows, maybe we'll get some guidance in the future. But until that happens, these are the numbers that I decided to use. And so that translates back here again, and just putting 0.25, 0.5. There's no data for BOD, so we're not going there, which is fine because neither OEPA or ODNR has been asking for that data. This has been part 3 of a 4-part day-long workshop on estimating pollutant loads using the U.S. Environmental Protection Agency's pollutant load estimation tool. Videos from other parts of the workshop can be accessed from the Hamilton County Conservation District's YouTube channel. A link to the playlist is provided in the description of this video. Thanks for watching.